Okay, let's get started. So as always, announcements first. So PA4 Bomb Lab, I've extended it for 24 hours based on the number of submissions that we've collected on Canvas, and based on what's going on Piazza, it seems like a good number of you could make use of extra 24 hours. So there's 3 sets of office hours tomorrow. So if you want to have additional resources, someone to turn to, those would be helpful resources. And as always, there's Piazza. So by now, there's many, many threads on Piazza that should provide helpful hints. Programming Assignment 5 is going to be released very soon. So just hang tight with that. I should have it out within the next 24 hours. So today, Tuesday, we're going to start a new chapter in the book, chapter 6, which is all about locality, right? So these are all very important chapters from this textbook, in the sense of like what, as a computer scientist, as a programmer, you need to know from computer architecture and what the hardware offers. This is one of those kind of underappreciated facts, like locality, caches, how to write programs so that it's efficient on the architectures that we have today. So today, Tuesday, April 5th, we'll talk about what locality is. If you want to follow along in the book, that will be sections 1.2, 0.1, 0.2, and 0.3. Thursday, we'll talk about caches and all the different policies around how caches are organized. And then next week, the 12th and the 14th, we will do, we'll wrap up caches, and then we'll talk about how you can write programs to take advantage of cache memories and how to write cache-efficient programs. Okay. So maybe we'll start with kind of a warm-up kind of discussion, right? So what is it that makes a program run fast, right? So what are factors that control the performance of a program? Well, actually, before we even do that, why is it important that programs have good performance? Why is that a good? Why is that an ideal case? Why performance? Yeah, in the back. Yeah, so the keyword I heard is time sensitivity. Right? Suppose that you're trying to make trades on the stock market, for good or for bad, right? And the time it takes for you to do the computation would have impact on many factors. And so the term for this is called latency. Right? The time it takes from you giving it an input to the time that the program finishes. This is called latency, and that's one aspect of performance. What other reasons is performance good? This isn't the only reason, there's more. Yeah. Energy efficiency. So energy efficiency. Could you tell me more about that? Yeah, right. So using less energy to do the same computation will save you your energy bill, would reduce the carbon footprint of a computation, would help address climate change given the same computation that you have to do. Right? Big data centers by the likes of like Amazon and Facebook and Google, among others, right? Their data centers, some of them actually literally consume energy on the order of a small city, and so doing the same computation, if they can do it with less energy consumed, that's a plus. All right, so latency, energy efficiency. What other metrics of performance are there? There's a specific word I'm looking for here, but I'm seeing if we'll come across that as a class. Scalability. Okay, so what is scalability? taking one program and being able to use it to affect a lot of people, a lot of data, right? So maybe the word I'm looking here is called bandwidth. Which is like how many requests can you handle in a given time, right? So latency is like given a single task that you have to do, what's the time it takes from input to output? And then bandwidth is given the same starting point, how much inputs can you give it that the program can finish within a given time frame? Right? How many parallel requests can you handle? Right? So what's the example of bandwidth, right? So we've all tried to download programs from the Bomb Lab server now, right? And so if you've ever come across a problem where the Bomb Lab server wouldn't serve your request, it just gave you a blank page, that's a bandwidth limitation, right? Multiple people are trying to request bombs from the Bomb Lab server, and it can't handle all those requests at once. We say that its bandwidth is limited. Okay, so these are metrics, right? So these are desirable things about well-written programs. What affects the performance? Right, there's a lot of things that affect performance now. What might they be? And the back. Hardware. Okay, so what about hardware? Okay, so narrow that down a little bit. So pick one, right? You mentioned several things. How well can the hardware handle memory? Okay, so interface to memory. All right, that's one aspect. How well can you interface with the memory? We'll revisit that. What other things affect performance? Maybe within hardware, right? So when we talk about, oh, this computer has good performance in terms of hardware, what's one key metric that we may consider? Yeah, clock speed. So what is clock speed? Okay, how many times a CPU, how many things a CPU can do, right? We experienced this very viscerally in this class already, right? So in GDB, what is clock speed in terms of what you see in GDB? A new debugger. Yeah, so each assembly instruction would be a tick, right? So basically, it's essentially how quickly the CPU can step through those instructions. This is the clock speed. This is controlled by the clock speed of the processor. Yeah, so these are hardware aspects. What about from like when we took 111 and 112? What are things that can control the performance of a program? Yeah. Okay, so we're viewing it from hardware now. So the number of instructions to get a desired program. Okay, so number of instructions. What controls the number of instructions that a program would need? Any other voices want to chime in? DJ? Aha, so the complexity. So what is complexity? Yeah, right. So is it a constant time algorithm? That'll be great. Is it a linear time algorithm, which is very nice? Is it a logarithmic time algorithm, which is very nice? Is it polynomial time? Or is it exponential time? Right. So this is what we study in a class like algorithms, and we touch upon in discrete structures. What is the complexity of an algorithm? Right. So you take an algorithm. It has different scalability with regards to the input size. And that's one big thing that impacts how many instructions it ends up being to do a computation. Okay, what are some things that might happen in between here, between the complexity and the number of instructions? Yeah, in the back. How strong the firmware is. So I don't know if firmware is the right term, but how well is the infrastructure? How well is the infrastructure going to do this translation from an algorithm, a very abstract algorithm, to a very concrete set of instructions? Right, so this is something like compilers and their optimization. Right, so how well it can take an algorithm and then translate it into a stream of instructions that's as short as possible to implement the same algorithm. Very good. Right, so we'll keep all this in mind. Anything else that we want to add to this picture just before we wrap up this brainstorming session? Yeah, what else do we miss? Yeah, so that's a good question, right? So what controls how good a compiler is? That's a very good question. And so, yeah, we can elaborate about that a little bit, right? So GCC is a very standard compiler that is commonplace. It accepts like the C language, among others. And it's a pretty solid compiler, right? But GCC, if you want to get it to really extract the best performance out of using GCC, there's a few things that you have to consider. When GCC was installed, it should be configured correctly, right? And we'll see maybe today what configured means, right? The GCC compiler has to be fed the right information about what's the computer it's compiling to, right? What's the memory size, what's the cache sizes, so that it can generate good code. The configuration of the compiler, there's other things too, right? So there are proprietary closed source commercial compilers that Intel releases, for example, called ICC. And ICC, what it does is it targets the very complex instructions that Intel offers, right? So we've seen how many, just like the mind-boggling array of instructions that Intel architecture, x86 architecture offers. And even the compiler developers for GCC don't really know how to use them all that well, right? Because it's just too opaque, too complex. But Intel, given that they know and they built their own processors, they can write compilers that target their own processors very well and extract even more performance out of it. So that's another consideration of the compiler, right? How well does it target the instruction set architecture? Okay, any other questions before we kind of finish up this brainstorming? Okay, so what we're going to move on to is a discussion about what's inside a computer, right? So we basically have studied processors, the CPU, the instruction set architecture really well right now. And there's more to it than that. A computer consists of other things like caches, memory, the storage hierarchy, hard disk drives, a connection to the internet, and other aspects, right? I/O devices, displays, and so forth. And these different components, they form a kind of hierarchy, right? So this is a picture that we call this pyramid here. We call it the memory hierarchy. And what it shows is several things, right? So first of all, like, where are we so far, right? So far, where we have done all of our studying is, okay, we've studied assembly language and how C programs compile down to assembly. And all of that so far, we've been at the top of this pyramid, basically. Right? From the view of the CPU interacts with the rest of the computer. What the CPU does is it executes instruction streams. Somehow, data and instructions just show up at the CPU. Right? So this whole hierarchy here is the mechanism with which like instructions and data is fed to the CPU, and the CPU outputs its results. And then the other note here is, yeah, so this is a kind of picture of the full stack of the computer. So what else should we say about this hierarchy, right? So organizing from top to bottom, at the top here, you have the very top of the hierarchy, where the capacity that you have access to is limited. Everything is expensive because it's very close to the CPU. Oftentimes, these are things that live physically on the silicon chip that implements the CPU. And so you're very limited in capacity. Okay, and then on the other hand, we have things like the internet, right? Isn't it kind of strange that we're putting all this together? On one hand, we have a CPU, and on the other hand, we have something as like vast in scale, like a societal construct as the internet. And it's very real, right? So the internet is enormous in capacity, exabytes, if not more, of storage and data and instructions and programs that you may have access to. And accessing all that data at huge capacity is extremely slow. Right? And in between here, we have all the layers that help the CPU, the program, interface with the world, right? The world being the internet, the network. And these different layers include things like caches. We'll study caches. The memory, right? So we're very familiar with the memory now. The memory consists of the stack and the heap, and storage, right? So things like hard disk drives. What we're gonna work toward is kind of understanding this picture here, right? So I put this picture here at the beginning of this sequence of the slides to kind of highlight what we're trying to work toward understanding, right? We're trying to understand what this picture shows, right? So what this picture shows is a kind of performance versus time, right? So performance here is the lower the better, right? By some metric here, the time it takes to access some data, and this is on a logarithmic scale, right? So every linear increment here is 10 times faster or slower. And so as time progressed from left to right in the 20 years plotted here, the time it takes to do some unit of computation has decreased for all of these different technologies. Right? And so the series of this plot are different types of components of the computer, right? So here we have the CPU. The CPU is the empty circles, so it's plotted down here, right? And it's followed this trend here from 1985 to 2015, where the performance increased from 100 down to 1/10, right? So a 1,000-fold increase by some metric. What are the other technologies involved here? So there's also SRAM, right? So this is what implements caches. And there's DRAM, which is what implements memory. And there's SSD and hard disk drives, all also plotted here. And some of the takeaways here, right? So one big takeaway is there's always this gap between storage and computation, right? So this always existed. The kind of other factor here is the gap between memory, right? So the shaded squares and the CPU, this gap has gotten bigger and bigger, right? So in 1985, by some baseline computation, right, some unit of computation, the DRAM, the memory, relatively speaking, kept pace with CPUs. And then as 20 years went by, CPUs improved and memory just hasn't not kept pace, right? So we're going to work toward understanding what this picture is and what are the implications of this picture. Okay, so the structure of what's going to come up is we're going to work through each of these devices and give a flavor of how they operate. Okay, so any questions here, right? So this is laying out the picture of what we're trying to understand, and we want to get a flavor of why this graph is the way it is. Yeah, DJ. Yeah, right. So summary of what this picture says, right? So look at the CPU, the empty circles and squares, the time it's taken to do some unit of computation that once took 100 units of time, now only takes one-tenth units of time. So it improved by 1,000-fold, right? And versus memory, right? So DRAM implements memory. The shaded square boxes here, the time it used to take, 100 units of time to load store some data. By now, it takes just over 10, right? So the time it takes to load store that data simply has not kept pace with how much CPUs have improved. And this leads to implications of how we write programs and how we structure computers to work around this difference in technology. Okay, sound good? Right, so the first component here is caches, or SRAM. Right, so this is these shaded circles here, right? So we've sort of studied how CPUs work. CPUs run operations. And so the next kind of general technology that we need to have an idea of how it works is the shaded circles here, SRAM. And what SRAM is, it's basically everything inside the CPU that keeps track of state, right? So what is state inside of the CPU, right? In GDB, what did we see that is the state of a program, the state of a computer? Different flags, right? Control flags, such as what? Zero flag, parity flag, above flag, and so forth, right? So that is certainly state, right? It is state that persists over time. It's some property of the computation of the processor that's true for that moment. What else is state inside the processor? And what else do we see that's also state? All the registers, right? So RAX, EAX, all the registers is state. It's a variable inside the processor. And among those registers, there's some special ones like the instruction pointer, which points at which instruction is about to be executed next. Very good. And that's about it, right? So that's about all the state that we've studied so far. Well, so clearly the state is very close to the processor, right? So the processor is literally working with the registers, doing computation on them, putting them back into the registers. And so all of this is implemented to be extremely fast, right? So this is all implemented in the form of SRAM cells. SRAM stands for static RAM, static random access memory. And essentially what it is it's some transistors that have been structured in a special way to create something that's bistable, right? So in the book, you'll see this picture that like nicely illustrate what bistability means is you have some pendulum, an inverted pendulum, which either wants to be on one side or on the other side. There is no stable state where it's exactly between. So it's either going to want to go to a 0 state or a 1 state. It's only stable in one of those two states. And essentially how it's constructed is it's the circuit here. The way to read the circuit is these boxes, right? This triangle thing with a little circle. This is an inverter. right? So the way to read what this says is you have a inverter, and suppose that you have some state here, say on this side of the circuit, it's a voltage value that encodes 0. Then the inverter is going to drive the other side. 0 becomes 1 on the other side. And this 1 here, this whole side is 1. And so this bottom inverter here is likewise going to take that 1 and drive the other side as 0, right? So the two sides are in concurrence. You see, if Q is 1, then not Q is 0, right? So this only wants to either have 1 or 0 on the other side. And it could be also the other way around, right? So the zeros could be on this side and the ones could be on the other side. The inverters keep driving the other side to be the opposite. The way you would read from this is there are these bit lines, which are then accessed by these word lines that allow the bit lines to see the state. And then likewise, you can also use the bit lines to force it into the opposite, right? So you can open up this SRAM cell, turn it on to accept values, and then use the bit lines to drive in charge to invert the zeros and ones, right? So there's a few things, other things to say about this, right? So because this is implemented with the same componentry as the CPU, it's very fast. It's the same technology as the CPU uses to calculate logic. It's also quite expensive, right? So every one of these bits needs 6 transistors to implement just storing 1 bit, right? So if you wanted some register file that stores like 64 bits and several such registers, you know, very quickly you're using thousands of transistors to create a whole register file, right? So this is expensive storage that's very fast. Okay, so so how fast? Well, the CPU is able to access this data, you know, every cycle. If not every cycle, then at most 10 cycles of the clock time. Any questions about SRAM? DJ. Right. So this whole construct here allows storage of 1 bit. Right? Is that expensive or not so expensive? Well, depends, right? Because it's registers and because this stores something like a 0 flag. Right? 0 flag may toggle every cycle of instructions. You know, it's extremely frequently used, and so it makes sense to use this expensive technology to store the state right next to all the logic that implements the CPU logic. Yeah. So the word line controls whether or not this SRAM cell is active. So you can see this is a transistor, it's a gate, it's a switch that basically says, is the state open to the bit line or not? Right, so if you're interested in this kind of stuff, this is like digital logic implementation, which is like a bread and butter of something like digital logic design in the ECE curriculum. Okay, so that's SRAM, which we use to implement registers, right? And then there's also memory, right? So where the stack is held, where the heap is held, when we malloc stuff, this is allocating some memory to store data, right? So main memory is implemented in a completely different technology, right? So this is called DRAM, Dynamic Random Access Memory. And the way that this works is it's essentially a capacitor, right? So we'll look at this picture here. Right? The way that this works is this is the kind of a cross-section of a DRAM cell, right? We've cut through vertically, right? You have this grid of DRAM cells, and we cut through the grid, and each one of these little wells and a needle inside, this is able to store 1 bit, right? The way that this works is it forms a capacitor between this plate and out here. and the charge on the capacitor plate stores the presence of a bit or no bit. There's a few things here, right? So the geometry of the way that this is set up, the way that the capacitors are vertical in this sense, allows them to pack the number of bits in the DRAM cell very, very tightly. And then the other aspect is the control of using this DRAM cell only needs one transistor, right? So this is a one transistor DRAM cell. All that transistor does is it toggles whether or not this DRAM cell is exposed to the word line. Right? So already we can see that it seems like this technology is able to pack in the storage more densely. And then overall, like what this is made of, right? These DRAM cells would be physically a different chip compared to the CPU, right? So the CPU will be made of silicon that's optimized to build logic and registers. And DRAM cells is a completely type of silicon that's optimized to make DRAM cells. Right? So this uses the two different technologies so that CPU can focus on working fast, and then DRAM can focus on storing vast amounts of bits on the given silicon area. So there's a few things here, right? So one is this is slower, and also this is not persistent. This charge over time will slowly trickle away. And so the DRAM cell, the way that the DRAM works, it constantly has to cycle through all the bits and basically read it out and write it back in just to refresh it. And this happens every tens of milliseconds. The computer is going through everything and just reading out all the bits, writing them back just so that it persists. The amount of DRAM available per machine is, of course, fast, right? So billions of bytes is typical for commercial computers. On the iLab machines, it has 1 trillion bytes available on the machine. Where can we find out how much memory does iLab have? Where did I get this information? Right, so have you noticed, like when you log in up here, there's a readout here that says this machine, what is this one? This one's iLab 3. Right now, 400 gigabytes are available out of 1 terabyte worth of memory available on the machine. Right, so already you can see like 1 terabyte, that's a lot more in scale compared to the meager registers that you have next to the CPU. Okay, we can go back to this picture again, right? So when we said that there's a gap that exists between DRAM and CPU, this is the gap that we face now, right? How long it takes to access 1 bit of data in DRAM in the memory versus how long it takes to access 1 bit of data in the CPU is this gap here. The order of about 100x, right? 0.1 versus about 10 or so. Here, it takes 1 cycle to access SRAM, and here it takes hundreds of cycles to access memory. So what does this mean, right? So is this bad? Hundreds of cycles to access memory. What does that look like? We kind of had a sense of this, right? So remember our instructions. What does that mean what does that mean on something like this? Move Q is an instruction. Move Q is an instruction, and suppose we want to do move EAX to EDI versus something like move Q percent EAX to this percent EDI. Which one works faster? Yeah. This one's faster. By how much or so? Yeah, 100 times, right? This is what I mean by it takes one cycle to do this from register to register in SRAM versus 100 clock cycles to go from this instruction out to memory. So I'm going to cut over to the textbook slides now to show what this looks like, right? So this is how things are tied together. We have the ALU, the CPU, right? This is where the instructions are executed. It talks to the register file, and then also the instructions can say sometimes you want to move some content in the register file out to main memory, right? So we can now trace through the actual instruction and see what this looks like, right? Suppose you have a load, right? So move Q A %RAX, right? So what it's trying to show us is something like this. Move Q %RDI to what it wants to do, to RAX, right? Saying move contents from an address in memory, say A, into RAX. And so what it has to do is, first of all, it has to move this address, right? So this is saying like the first step is the CPU over here, the ALU has to send via this interface to the memory an address, right? So it's sending A all the way to main memory. Main memory has to operate these cells, right? Open up the right word lines, access the right bit lines, load whichever address, whichever cells are at this address, so that the contents, which they call X, is loaded up and sent back via the bridge into the bus interface on the motherboard through the various chips that intervene, and finally puts it inside the register file here, right? So now the CPU has that content, X, stored ready inside RAX, right? And then writing is similar, right? So writing is, suppose now we want to take data from RAX and store it into the main memory. Again, same idea. First, you have to put the address, A, right? So this address may be something like this. Send it over to the main memory. The main memory, in response to that, will use these transistors to open up the right cell, expose the right capacitors to receive the data. And the CPU then puts the data, here the data is Y, onto the bus over to the main memory. And the main memory puts it inside the DRAM cells like so. Right? So that's all the steps needed to actually implement a simple instruction that looks like this, right? This one instruction requires the coordination of the CPU, the main memory DRAM cells, the memory controllers, the motherboard, the North Bridge chip, just to implement this one instruction, right? So you can see that this starts to get pretty costly and slow. There was a hand here somewhere? Yeah. So all this is parallel, right? So it's able to send address, all the 64 bits of the address in parallel, and then send the data in parallel. There's a lot of different standards, right? So the textbook kind of has a few pages that enumerates the various generations of DDR, DDR2, DDR3, DDR4, and so forth, right? And the textbook's already very out of date in terms of the standards that they create so that the interface to main memory is standard across different vendors. Right? The CPU knows one protocol how to talk to memory, and that protocol says exactly how you put the data into the memory. Good. So that's DRAM, right? So this is how main memory is implemented inside a computer. So this is kind of to put that into a more concrete picture. This is that same picture that we borrowed from the textbook, right? This points out the various pieces of it. The CPU itself has a memory controller, which is called the bus interface here. And this is a sizable amount of real estate on a real CPU chip, right? So this is a 2020 Intel chip that implements x84-64, right? So it's an x86 chip. And the memory controller here is all of these transistors, all the silicon real estate dedicated to performing the protocol, which is called DDR4. It's a standard interface to main memory. It talks this protocol to the I/O bridge on the main board, on the motherboard of the computer, which then has connections to the main memory. Right? So the CPU here and the main memory, again, are implemented in different technology. They're physically different chips, and that allows them to optimize for different objectives. CPU is for speed, main memory is storage density. Any questions up to here? Right? So up to this point, we've talked about the various points from CPU to caches and SRAM here, and DRAM. And next, we'll talk about what storage looks like. How many of you have held memory in your hand before? What does memory look like? Yeah, what does memory look like? What am I talking about here? When I say memory is a different chip, like what does that physically look like? Yeah, it looks like a harmonica. Basically, right? I don't have a picture of it here, but we go look it up, right? These little DIMMs that each of them is like, say, 2 gigabytes or 4 gigabytes or 8 gigabytes of memory that you can slot into a desktop computer. Okay. Unfortunately, these days, everybody uses laptops, and so it's kind of a bygone era that you get to open up a computer and kind of move things around, right? Even laptops don't allow you to swap memory anymore. But this is all like tangible stuff, right? Okay, storage. All right, so storage is yet another layer of this hierarchy here. There's two main technologies that implement storage. One is solid state disks, SSD, solid state drives, and the other is hard disk drives, HDD. The main thing to know about this is, well, it's even slower, right? So whereas it takes about 100 cycles to get to memory, if you wanted to open a file and open it from the file system, have the operating system coordinated and put some data into the memory, it takes 100K CPU clock cycles. This line here, right? Accessing storage. Did we do this yet? Where have we done something like this in this class? How does this connect to the programming assignments? Yeah. Yeah, this is what's the function name that we're talking about here? scanf. fopen or file open, right? So that's actually saying open a file name, like something you take from the command line. That file is on a storage drive, on a disk drive somewhere, and saying, go look for that file. Tell the operating system, go look for that file, and load the contents into memory so we can work with it. Right? So that line to say open a file and put it into memory, this takes hundreds of thousands of clock cycles to get a single bit. There's a few reasons for why this is slow, right? First of all, it's just yet another device technology optimized for yet further storage density, right? So all this SSDs, it's more transistors, and those electronics are optimized to store terabytes of data per chip, right? So whereas the main memory was optimized to store gigabytes of data, here we're talking about terabytes of data in any given chip. The older storage devices, these were actual physically spinning hard disk drives, right? So if this is something that you're interested in, right, the follow-up classes to explore how the file system works and how the operating system coordinates using a file system to coordinate these technologies, that will be systems programming and OS. All of this is tied together with yet more buses, right? So before we had this picture here of CPU and main memory. They talked through the motherboard, through the Northbridge chip, the interface between the CPU and the main memory. Well, all of these other things, like storage, hangs off of yet another bus, right? So all this hangs off of a peripheral bus here, which then connects to various things like one, your storage, display, and input-output, right? The keyboard, mouse, and so forth. And again, this is other kind of things about how that's all connected together. And a lot of this, if you're interested in something like networks on chip and how these protocol work, that will be a class like Internet Technology Networks. Any questions up to this point? Here's this, right? How many of you have held a physical hard disk drive before? And yeah, were you sure it was a hard disk drive or a SSD? Yeah, so it's actually, how many of you have opened it up before? It's a fun exercise. If you ever have a broken hard disk drive, you can open it up. You'll find all of this inside it. You'll instantly have ruined it. But there's a few kind of interesting things here. There's like these really strong magnets that you can take out and use them as refrigerator magnets, among other things. Right? Anyway, so this is to kind of help us understand this picture here, right? So storage has always been slow. The kind of emerging trend here is even main memory is pretty slow compared to how much CPUs have sped up. Right? And so this is the CPU memory gap that we need to work around. Any questions up to this point? What are we going to do next? So what we'll do next is an illustration of why this gap is bad, right? I've been saying that there's this gap between memory and CPU. Let's now do an exercise to experience that in action. So unfortunately, this example code is not pushed to the repository yet. I'll push it later today. But this is going to be in a folder called Sum Array in the Programming Assignment 5 directory. This is not a programming assignment component. This is just kind of the example code. So let's look at this code here. Right, so somebody want to tell me what this function does? Sum array rows. Yeah, what does this function do? Sum of elements of each row. Not quite. What does the whole function do? What is the return sum going to be? Yeah. Sum of a 2D array, exactly. Right. So we've got a 2D array here. 2D array. The actual dimensions of this array are how big? Is shown on the screen right now? Yeah, how big is the dimensions of this array? M by M, right? What is M right now set to? Yeah, 1024, right? So how many elements are in this array? How many numbers, or about how many numbers? Yes. Yeah, about a whole million numbers. It's a big array. Right, so that's the input, an array of size 1024, and it's a nested loop. Iterate across rows, iterate across columns, update sum to have the increment by the value in each element of the array, and then return the value. Okay, so that's sum array rows. What's sum array calls do? Yeah. Yeah, so same function, but what's different here, right? So what's different here is instead of iterating through I first, here I iterate through J first, right? So to put this in context of this picture, sum array rows travels through this matrix, this 2D array, by going across the rows and summing through the elements like that across the rows. The sum array calls does the opposite thing. It goes through the columns and traverses through the array vertically. Make sense? Okay. So they do the same thing, right? So we have this picture here. Things that impact performance. Is the complexity any different? Same complexity, right? It's actually pretty much the same algorithm. Is the compiler going to be different? And we're going to use the same compiler to compile all this, right? So that doesn't really change. Is the number of instructions different? It should compile to the same number of instructions, generally speaking, right? The same complexity, same compilers. It should result in an instruction stream that takes about the same number of instructions to execute. Is the clock speed any different? No, clock speed, right? Same, right? So this is all going to run on the iLab CPUs. We're not going to, run one program on one CPU, another program on another CPU. So the clock speed, the speed at which the CPU can execute instructions is going to be the same. So, okay, it seems like it should be all generally the same, right? So let's do that experiment. Okay, skip over this for now. This will be coming in next week. But now we're in the main function. And here I'm going to demonstrate timing a code. How many of you have timed your code before? That's something that we did in 111, 112. Some nod, some no. Right? So how do you time code? Timing header, okay, this is in Java. Okay, suppose that there's a time header of some sort, right? How do we time code? Mm-hmm. Yeah, exactly, right? So in C here, we have facilities to time code, right? So it's called this clock function. Clock, what it does is it actually reads the, I don't know what register it reads exactly, but on the CPU, there's a register that records how many clock ticks, how many clock cycles have elapsed. And what you do is record the number of clock cycles at the beginning of your program function that you want to time. And then once it's done, you record that number again. And you subtract the two values, ending clock time, starting clock time. And then you divide by a constant called clocks per second, right? So this clocks per second varies widely across different computers that you're using, but calculating this will give you the wall clock time, right? So this will give you the physical seconds it takes to execute some array rows. Right, so the rest of this main function here, well, we're initializing a array with random numbers, and we're going to sum the array with sum array rows, and we're also going to sum the array with sum array calls. So, and then we check that the two results are the same as a sanity check. The two results should be equivalent. So let's go ahead and compile this. Makefile again. Right, so we're using O0, no optimizations in GCC, and we're going to compile and run this program. Right, so we compile and let's run. Right, we can do this a few more times. Right, curious. Right, what's curious here? What's faster? Which one's faster? Yeah, the rows version is faster, and very consistently so, right? And one other thing that we should double check is, well, maybe there's kind of some preference here, right? Maybe it's better to go first. So let's reverse it, right? Instead of doing sum arrays rows first, we'll let sum array calls go first, just to make sure that, you know, whichever comes first is not somehow making a difference. Yeah, so now we have calls going first. And let's let it run. And still, right, so we reverse the order of the two, and rows is consistently faster. Right, and we already agreed that all this is the same, complexity is the same, compiler is the same, instructions should generally be the same, the clock speed of the CPU is the same. So why do the two have different performance? Anybody want to kind of leap ahead and kind of guess why that's so? Yeah. Yeah, right. So the way in which this is stored in memory, right? So the way in which this array is stored in memory is going to be, well, memory doesn't have this 2D structure to it. Memory is just a long sequence of addresses, and each address stores a byte, right? So this array here is physically stored right, so I'm dividing this into 16 boxes here, right? So the array is actually stored like that, right? It's stored in this sequence here. Each row is kind of in its own little sequence, and all the rows are just packed together, right? I drew this divider wrong, but okay. Now suppose, that's bad. Let me draw in the dividers for the rows in the right place, because that's helpful. Right, so one row is stored up to here, the next row is stored up to here, the next row is stored up to here, and the last row is over there. So what's the order in which sum array rows traverses this array? Well, sum array rows just goes row by row, right? So it's basically going through this array just like straight through. And how does some array calls go through this array? Yeah, it jumps 4 at a time, right? So some array calls, instead of going once through this nice sequence of memory, some array calls starts at 0, goes to 4, goes to 8, goes to 12, comes back to 1, and then goes to 5, and then goes to 9, and so forth, right? It jumps around this array. And so that seems bad, and we need to understand why exactly that's bad, right? So any questions with this demonstration so far? Yeah. That's a good question, right? So when you're reading memory, does it somehow, what's the term that you used? Pull multiple data, right? Exactly, right? That's exactly what's going on. When you read memory, instead of just reading the only one byte that you care about, it pulls a chunk at a time, right? So this pull multiple data chunks at a time, that's exactly what caches do, right? So that's what we're working toward understanding. Sure, right? So if the array was small enough, would there be no difference? Well, we could experience that. Let's say, well, it's kind of tricky because as we decrease this, the difference will be less significant, but we can try, right? So let's decrease, if we make the array small enough, would it not make a difference? Sure, let's try that, right? So let's make this, say, 128 by 128 only, a smaller array than before. And we'll run it. Well, okay. So it's saying that calls is consistently slower. But this time around, maybe we can do one thing, right? So maybe we can swap the order of rows and calls again. Right, let rows go first. It's still the same, right? So rows is still a little faster than calls, even if we switched it around, right? But certainly, as you make the array smaller, the effect should get smaller and smaller. Exactly, right? At some point, if this array was just 2 by 2, right, it's a tiny little 4-number array. Each of the 4 numbers is 1 int, so 16 bytes. Well, then that whole chunk will just fit in one read. Okay, so what this is illustrating is a key concept called locality, right? So locality has 2 flavors, spatial locality and temporal locality. And it's an important concept to create this illusion of fast access to capacious data, right? What we want is we want to have this illusion of from the CPU, you can access the huge amount of data available in solid state or hard disk drive storage, but have the illusion that that data is accessible instantaneously, right? So this is being enabled with this concept called caching and locality. And locality is a property that caching takes advantage of. Right, so here, that's exactly what we've done from the perspective of memory hierarchy. Locality is this concept that you would use data in any particular level more frequently than the next lower level. Okay, what does that mean? We experienced this in sumarray.c just now. We compared how fast sumarray rows versus sumarray calls are. And rows versus calls, this demonstrates a difference in how much locality each function has. And you should write programs that maximize locality, have more locality than no locality. So concretely speaking, there's 2 types of locality. One is spatial locality. So spatial locality. Let's see. Let's use a kitchen analogy, right? In a kitchen, where should the spices be located? Spice rack. Where is the spice rack usually put? In a sensibly laid out kitchen, where would you put the spice rack? On the counter next to what? Should it be next to the sink or should it be next to the range? Okay, I don't know how your kitchens are laid out, but you would put the spice rack next to the range, right, where the spices will be used. That's what spatial locality is, right? Putting things adjacent to where they would be used next, right? So in this example here, this is a dot product program. We're going to find the dot product between two arrays, A and B, of size n. And the dot product basically multiplies the contents of A and B and adds it, right? So the spatial locality here is you have two arrays, A and B, and this program has a tendency, once you've accessed A element 0, the next element that's going to need is A element 1 and A element 2. It's just like here, right? So this array here, the spatial locality was that once you're done with reading 0, you would next read 1 and then 2 and 3. This is spatial locality. This is one type of locality. The other is temporal locality. All right, so temporal locality. So what's the temporal locality example in the kitchen again? How about think about this, right? So at what times are the refrigerator door open in the kitchen? Like if you were to take a kind of like a distribution diagram, probability diagram of, morning to midnight from 0 a.m. to 0 a.m. and noon in the middle, and you plotted all the times the refrigerator door is open, what would this plot look like? To take a guess, right? Is it going to be uniform? Is it going to just be like random points in the day? There's an equal probability that someone's going to go open the refrigerator door? Yeah, maybe there'll be peaks, right? So like in the morning, people wake up, get breakfast, another around noon for lunch, and another around dinner time, right? It's correlated with itself, right? So this is temporal locality. Once an event happens, there's a high chance that it's going to happen again around that time, right? It's not uniformly distributed, sure, like in the middle of the day, random points, maybe somebody will go take a peek or something, but for the most part, the time at which the refrigerator door is open is going to be in these peaks. This is what this is illustrating, right? You have this program here. It has the function dot product. You have a variable called sum. And in the whole picture of this program here, this variable sum, it's going to mostly be accessed around the same time, right? So when sum is accessed here to start summing this array, the dot products of this array, these two arrays, well, sum is going to get accessed continuously every iteration of this loop for n times until sum is done and never used again, right? This is temporal locality. Program data tends to get accessed over and over. And the key here is, all right, programs have spatial and temporal locality, right? And this property is what's being exploited to create the solution that you can access data very quickly. Any questions up to this point? Right, so we've talked about spatial and temporal locality. Where else do we have locality, right? I've mentioned how locality is exploited up and down this hierarchy, right? So let's use this picture now. So what I've demonstrated is there's locality between how the register accesses main memory, right? So when the register needs to access the array elements, it tends to have spatial locality. When the registers need the data in sum, again, it happens temporally close to each other, temporal locality. Where else in the stack, right? So is there locality between storage and internet? What does that look like? What would be an analogy there, right? So the locality when you access the network. Yeah. Yeah, so physical location, right? So maybe instead of like going to the internet example, right? So here, I'm using CyberDuck, right? I'm accessing files inside the file system on iLab. And there's spatial locality when I first accessed some array.c, and then the next file I needed was the make file. This is spatially close to each other. What's an example of temporal locality when we access the network? Yeah. Moving into the file? Oh, no, that's not quite temporal. I don't know what you mean by that. Temporal, remember, we're talking about temporal in the sense like correlated access in time. So yeah, there's an example here, right? So if you look at the load diagram of iLab machines, how much network load the iLab machines face, it's peaky, right? So usually most of students start doing homework on iLab machines just after classes and before, say, midnight, right? So that's a kind of temporal locality of when the network resources are used. Okay. So just a few minutes left, right? So what I'll use in these few minutes is I'll go through these two slides just to close out this idea, right? We talked about how memory is grabbed in chunks. Well, memory is grabbed in chunks exactly via this concept here, right? So when the CPU goes to main memory and asks for data, it doesn't just give it one element at a time, but instead it gives it chunks at a time. And these chunks, basically, the data comes in and it gets stored in what's called cache memories. And cache memories are very important and they occupy a lot of real estate, right? So there's a lot of dedication to having caches. So here's, again, a real picture of a CPU chip. And you'll notice that, okay, the actual logic for doing the arithmetic, the registers, so forth, yeah, that's a sizable part of the CPU, but a huge part of the chip are these arrays called caches, right? So the caches are what hold these chunks of data at a time. And so the picture here is when you access some larger data, right? So from this level here, we're going to access the memory. The upper level is smaller, faster. So this is like the registers of the CPU. Down here, this is like main memory. It's more capacious, but slower. When you move data, whole chunks are copied at a time, right? So this is the cache idea. And what we have to talk about now is when the CPU tries to go access the memory, it has a few possibilities, right? So a few possibilities is, first of all, it finds the data in the cache, which would be called a cache hit, or it doesn't find the data in the cache, would be called cache miss. And so instead, it's going to have to go look for it inside the memory. Right, so the next few sections of this class would be about how caches are organized. And so there's a few questions around how caches are organized, and that's going to be, we'll start talking about that on Thursday and on next Tuesday. All right, So I think that's a good place to wrap up here today. Any questions? I'll be around. Otherwise, good luck wrapping up on Bomb Lab, and PA5 should be out pretty